Okay, in this video, we want to go over how to graph something like dy dx equals x minus y, and we're going to look at another differential equation as well. You'll notice this differential equation, it's called a first order differential equation because there are only first derivatives. Second order differential equations have second derivatives in them. We're not going to go anywhere near those yet. So here is a first order differential equation, and we can graph it out. All right, so to graph it, notice this is not an equation y as a function of x, so it's not a line. We need to represent this as a slope field. So let me draw a little set of x and y axes. Let me put the origin right about there. So we'll only go a couple of units over and up because this is a long, tedious process, and we're not really going to do many of these by hand, if any at all, because computers are very quick at generating all of the points. So what we want to understand is how does the computer actually generate those points for the slope field. All right, so if I wanted to figure out what this looks like, I need to pick a starting place and then just work up and down from there. So let's start at 0, 0. So if you were to look at x equals 0, 0, right at the origin, dy dx would be 0 minus 0, which is 0. So what we want to do is actually draw a little tiny line that has a slope of 0. So a little line segment with a slope of 0. Now let's go up 1. If we go up to the point right here, which is 0, 1, then the slope will be negative 1. We simply put 0 in for x and 1 in for y, and we get that the slope should be negative 1. If we go up 1 unit higher, then we're at 0, 2, so we have 0 minus 2. So our little sloping line segment has to have a slope of negative 2, all right? Now, you don't need to be super precise here because it's kind of hard to judge by eye the difference between, and a slope of negative 1, by the way, let me draw a diagonal like this, see over here, has a slope of negative 1. It's a 45-degree downward sloping line. A diagonal that goes the other way would be a slope of positive 1. So it's relatively easy to judge what a slope of 1 looks like. Just make sure 2 is steeper. So negative 2 is negative and steeper. And then when we go up 1 more, it would be negative 3. Just make it steeper, right? Now, we would keep on going. We could go down to 0, negative 1. Oh, well, that would have a slope of positive 1 because it would be 0 minus negative 1. And then a slope of, I maybe made that a little too steep, and then a slope of positive 2. And following the trend, a slope of positive 3. All right, now let's go over to 1, 0. So we're just sort of stepping our way through the graph. If we go to 1, 0, well, x is 1 and y is 0. So that would have a slope of positive 1. Let's go over to 2, 0. Oh, that would have a slope of positive 2. And 3, 0 would have a slope of positive 3. Maybe my 2 was a little bit too steep. Okay, so you can see the slope gets steeper and steeper as we go to higher and higher x values. Now there's some interesting places, like if we go to the point 1, 1, that has a slope of 0. And so there are actually some interesting patterns in here. So does the point 2, 2. So I can put in some slopes there. And so does the point 3, 3, as does the point negative 1, 1, negative 2, 2, and negative 3, 3. So we can more quickly put in some lines if we look for trends, all right? If we went down to negative 1, negative 1, let's see what happens there. If you have x equals negative 1 plus y, oh, that will also be a slope of 0. Negative 2, 2, slope of 0. Negative 3, 3, slope of 0. And we can do the same thing here. Oh, I need to be careful now. If I go upward, oh, those are all wrong that I just put in. Let me change those. Those were positive x's. So when x is 1 and y is negative 1, that should have a slope of 2. It's 1 minus negative 1. I thought something was odd. So that should have a slope of 2. And if we go down 1 more, the slope goes to 3. And if we go one more, the slope is even steeper at a slope of 4. It's kind of hard to start to illustrate how steep that is. Okay, and then if we were to work our way up this line, we go from 1 to 0. It's going to be -1 next, and then -2. And if we work our way up here, we had a, if we start at x equals 2, 0, and work our way up to 2, 1, the slope drops to a 1. And then we hit our 0, and then we would have a slope of -1 just above that. And if we go over one more to starting at 3, 0, we can see that we would go up 1, and we would have a slope. We started with a 3, so it'll be a 2, and then a 1, and then a 0. Oh, so this looks like an interesting part of the graph right here. Whoops, let me change colors. Okay, so we have something interesting going on here. This is where the slope line is 1, so these slopes are pointing at each other, those little slope lines, okay? Well, if we continue down here to x equals -1 and y is -2, that would also have a slope of 1 and a slope of 1 here. So we have a series of slope lines that would point to each other. We'll see later on when we go to graph some of these equations, that would actually represent an asymptote. It's a diagonal asymptote for the solution. All right. We'll talk about how to sketch solutions in a little while, but that is that line has a pattern. Now we could keep on going and keep sketching these points by hand. I'm just going to throw in a few more. We can see as we go to the left, they get steeper and steeper in the negative direction, steeper and steeper. So we have something going on like this, and we could fill in a few more down here. As x gets bigger, the slope becomes more positive and even more positive. Slope becomes more positive and even more positive. It's kind of hard to differentiate between how steep they are once they reach a certain steepness, all right? But we can almost see a little flow in here. We're going to talk about this later, of these like lines kind of curving towards this asymptote. All right, and we'll talk about how to sketch the solution, y equals f of x, into the slope field depending on where we start. So if we have different starting points, our solution through our slope field may look different, but we need to be able to first generate the slope field. Now you can see that's time consuming and tedious. So we might want computers to do that for us. Let's look at one more by hand and talk about the trends of this one as well. Let's look at dy. Let's look at x times dy dx is equal to y. Well, we can't sketch the slope field until we solve for dy dx. So we would want to rewrite this as dy dx is equal to y over x. So remember, dy dx will be the slope value at any point. So we need to put x and y values in to determine this. And you can see, even if I just limit myself to going up 3, down 3, 3 in every direction, that's a lot of points to look at. I believe it's a total of 49 different points because there are 7 points from -3 to 3 in the x direction and -3 to 3 in the y direction, or 7 more points. So 7 by 7 gives me 49 points that I would have to map out. So we don't want to do too many too slowly, or by hand, because it takes a while. But let me just do a few. So first of all, division by 0 leads to something that's undefined, but the origin is even more special. I'm just going to put a little circle there because that's a division of 0 by 0. So the slope field is completely undefined at the origin, all right? Now let's consider if we keep y equal to 0, then the slope needs to be 0 everywhere except the origin where it's totally undefined. So wherever y is 0, the slope would have to be 0. We're just looking at the integer points. There obviously, the slope exists everywhere in between, but just like when you're drawing a graph by plotting points of it, you just take a limited number. All right, then if we keep x equal to 0, when you take any y value that's not 0 and divide by 0, you get an infinitely steep slope. So you can see what we talked about, in the previous graph. There's an asymptote. Those slope lines are pointing towards each other, and these slope lines are pointing towards each other. So there's a vertical asymptote along the y-axis and a horizontal asymptote of the x-axis when we put in our slope field. All right, now let's look at some other places. When y equals x, the slope needs to be positive 1. So these are all of the places where y equals x. So we can put those slopes in pretty quickly. If we look at the other diagonal, this is where y is the negative of x along this diagonal. So we can see that at a point like 2, -2, the slope has to be -1. All right. So once again, these look like they might be asymptotes here. Okay, so I have an asymptote there, and I have another asymptote here, where the lines, the slope field lines, point to each other. All right. So interesting things will happen if I'm along one of those lines. All right. Let's keep on going a little bit. Actually, let me just pause and collect my thoughts for a second, and then we'll keep going with this. Okay, so we're going to flesh out the rest of the first quadrant. So at the point right over here, 2, 1, that would be a slope of 1/2. All right. When I get to a 0.31, the slope goes to 1/3. All right. If I move up to the point, it looks like 3, 2, then we're looking at a slope of 2/3. All right. And if I come over here to the point 1, 2, the slope should be 2, and then the slope should be 3 right above that, and then the slope should be, you can start to see what the slope field should look like. All right. Now, if I work down here and I go to 2, -1, that's a slope of -1/2. So it's kind of the mirror image. I could take the first quadrant and flip it over the x-axis, and I will get the values that I should have. This would be a -1/3, and then something that's a little bit steeper here. Okay, and I can take those slopes from up above. Whoops, I think I didn't do that. No, this one. Whoops, this one should be going like that, and this one should be going like that, and this one should be going like that, and so on. And we can sketch what the slope field would look like. And then we could actually take this quadrant and flip it the other way, and we would see what happens when we're over there. If we take the mirror image of the points that we had graphed here, we can start to flesh out what it would look like elsewhere. All right. So that's how we would generate the slope field for dy dx equals y over x. And you can see it's a time-consuming affair, so we're not going to spend a lot of time doing that. Just each one of those little mini segments is a line segment that has the slope matching, in this case, the y divided by x value.